right, so I'm live with 52 weeks of AWS, and I'm continuing down the AWS machine learning certification route here. I'm going to be talking about implementing a machine learning pipeline with AWS SageMaker today. So there's a lot of detailed information about SageMaker, and really in a nutshell, if you are going to be studying the AWS machine learning certification exam and you haven't gone deep on SageMaker, you're going to have some problems. And that's really one big takeaway from the very beginning, is to use in an interactive way SageMaker so that you can do your best in learning really the premier platform for doing machine learning on AWS. So I'm going to go ahead and get started here and talk about this. So really to get started here, I'm going to kind of dive into some of the details here about pipelines, talk about scenarios, collecting and securing data. Really, this is a critical thing. Integrated security, evaluating data, pre-processing data, training, evaluating the accuracy of a model, talking about hosting and using the model, right? This is more of the MLOps stuff, hyperparameter model tuning, and also talking a little bit about some of the things you can do with SageMaker Autopilot. So let's go ahead and get started here. With machine learning, one thing that you can really consider when you're going through and building something out is this concept of the pipeline. You know, in section 1 here, problem formulation. This is really the beginning of you architecting things out in a way that makes sense. If you don't have the proper way of architecting or formulating the data, the problem, you're going to have an issue doing anything else. Likewise, in section 2 here, we talk about obtaining and securing the data. We talk about evaluating the data. Section 3, section 4 is feature engineering. Really important to deal with using the right signals for the model. And then finally, we get into these other sections here. So we can dive into all of these in a little bit more detail. And in particular, I think what's important here is to talk about the whole pipeline as a collection of tasks, right? Not just by itself. And so to start with here, you need to think about how to turn a business problem into a machine learning problem. And that's really phase 1. And the first step to do that is to define the problem you're trying to solve and the goal you want to reach. For example, how is this task done today? And then how would I use the business measure to measure whether it's successful? And we see this with startups, right? 2022 may be the year that a lot of tech startups crash. And I think one question is, how are these businesses measuring their success? Is it growth at all cost, or is it build a useful product that's profitable, right? Sometimes those can be in conflict. Also, how will the solution be used? Are there similar solutions that exist, and can you learn anything from it, right? If you are trying to build something, I think one of the best things to do is look at a reference implementation, especially for machine learning. Also talk about the assumptions that were made. Like, are you assuming, for example, that you'll raise $100 million every year, right? That's an assumption that if it doesn't hold up, you could have problems. Who are the domain experts? So if you're going into medicine and you say, for example, we're going to get rid of radiologists tomorrow, and you haven't consulted with radiologists, then you could have a problem implementing AI. And I think we see this a lot with machine learning and AI, is that a lot of people have been very aggressive about predicting the end of some industry, taxis, healthcare, et cetera, and they just didn't bother to talk to the domain experts. So I think people are starting to learn that you're going to have to talk to the domain experts. Now, how do you frame the problem? I think this is really critical. Is the problem a machine learning problem, right? Like, what if it isn't? In the case of maybe something that's a business analytics problem, potentially all you need to look at is the mean, right? Or the median, or the geometric mean, right? Like, there could be a metric that you could use, and you don't need to do machine learning. Once you do decide that it's machine learning, Is it supervised, unsupervised, or reinforcement, right? That would be the category that you need to dive into. With supervised, you have historical data. With unsupervised, you're really discovering things. Reinforcement, you're using an agent that you're feeding rewards to. What is the target to predict? I think this is, even though it seems kind of simple or trivial, this is something I've seen a lot in machine learning projects where there's issues initially getting started, is that you can't just do exploratory data analysis forever. It's important to do some, but at some point you have to say what it is you're doing and have a very specific recommendation, right? I'm going to predict this amount of revenue in Q4, or I'm going to predict the correct product to recommend to a customer, right? You need to be very, very specific when you're doing a prediction. And then also, do you have access to the data, right? Like if you don't have access to the data, you could be dead in the water, right? You won't be able to solve it. What's the minimum performance? And then also, how do you solve this problem manually? And also, what's the simplest way to do it? I think it's very, very easy. If you look at Kaggle, for example, in a way, Kaggle is the most complicated way to do something. And that's why I think in many cases it doesn't represent a real world scenario. In the real world, you want to have the simplest solution initially and later figure out whether you even need to do the complicated solution. So here's an example of problem formation. Let's say you want to identify a fraudulent credit card transaction. And so you can stop that before it even processes, right? That's the goal here. And so what's the business outcome? Well, the intended outcome is a reduction in the number of customers who call up your company and say, hey, I'm having a stolen credit card problem. From a business perspective, one of the things that you would want to do to define your success is that potentially you would want to say, I want maybe 10% reduction in the number of customers who file complaints for fraudulent transactions within a 6-month period. So notice very, very specific statements in the problem formation. Now, how do we make this a machine learning model? Well, one of the things that you can do is also get very, very specific here, right? Either a credit card transaction is fraudulent or it's not fraudulent, right? And you're not breaking this into a million different categories, exploding the complexity right out of the gate. You're making it simple right out of the gate, which is either it's good or it's bad, right? Is it fraud, not fraud? This is a binary classification problem, something that machine learning is very good at. How would we build this model? Well, you would go through and use historical data to look at the different results and train the model on the historical reports of fraud or not fraud. Another thing to consider would be, let's say, the wine quality data set. Based on the composition of the wine, could you predict the quality and therefore the price? I think this is actually something I care about a lot. I like drinking wine, and I always want to know, should I buy a $30 bottle of wine or should I buy a $5 bottle of wine? How do I know? And so this case, you want to look at statistics, look at outliers. You have to scale the numeric data. In almost all cases, when you're dealing with machine learning, you must scale the data. There are a few situations like decision trees where you don't, but in general, you want to do that. And now the data sets are very actually interesting. I'm actually a fan of Portuguese Vinho Verde wine myself. Very, very nice, light, kind of white wine to have with a dinner. But Portuguese Vinho Verde wine is one of the data sets. And you're able to actually look through this and figure out what is the proper pricing for this wine. Car evaluation data set is another one. And in this case, you could say the question would be, can you use a car's attributes to predict whether the car will be purchased, right? How would, we would look at the statistics, and we'd also need to take the data and turn it into a numerical form. So that's one of the other key aspects of machine learning, is that not only do you need to scale the data for the most part in most situations, but you always need to deal with numerical data. So if it's in a categorical format, you have to convert it to a numerical form. There's also a vertebral column data set. So here would be the way to formulate the problem. based on the biomechanical features, can you predict whether a patient has an abnormality, let's say a disc hernia or a very fancy name, spondylolisthesis. I don't know if I pronounced that right, even though I did take a year of anatomy and physiology. Uh, and then you would look at the statistics, you would encode the categorical data, you would train and tune the model. So that's a good kind of refresher here on how to think about converting things into a machine learning model format, and also what kind of model are you going to train? Classification, right? Binary classification or regression, right? These are good examples. Okay, let's talk about collecting and securing data next. And so in this section, we're going to dive into that category. So what is the data that you need to solve a problem, and where is it? Do you have access to that data? And then also, what is the solution that you can use to bring all this data into a centralized repository? Now, I think this is a very critical one, because a lot of times people that are doing data science don't use cloud computing. So I would say this is one part where you have to really start thinking through the problem and saying, well, we may first need to even set up cloud computing to even solve the problem. So in terms of data sources, the private data could be data that the customers create. It could be commercial data. So AWS has AWS Data Exchange, AWS Marketplace, other providers. Also open source data that's publicly available. It checks for limits on usage. A good examples of open source data would be Kaggle, World Health Organization, the Census Bureau. For example, the Census Bureau has some really good information about demographics, national oceanic and atmospheric administration data, NOAA, UC Irvine Machine Learning Repository, AWS. Also, Hugging Face is a pretty good example of a data set location. And then with machine learning, you need to have observations. And so machine learning problems need a lot of data, also called observations. And so in this case, where the target or prediction is already known, right? So that's the whole point of supervised machine learning, is you have the right answers and you're going to train your model on those right answers. And this is the labeled data and the target and the feature, right? The target is what you're going to try to predict, and the feature is what's going to drive that prediction. There's the target here. In this case, we want to predict what this would be, and the features would be the vendor and then the charge amount. So this is the other part that's critical, is getting the domain expert. So again, we've seen so many different examples of really elite level people in AI and ML claiming that they can get rid of radiologists, claiming that they can make self-driving cars, claiming they can build, sentient AI, all this stuff. But in reality, what they may have missed was actually talking to the experts. In case of data science, you really do need to talk to an expert to figure out what it is you're trying to do. And if you don't include them, you're going to have a very difficult time understanding what good is. And so they would be able to tell you the data you need, right? That they probably have some really good insights. Like, for example, in the case of a hospital, the nurses, the doctors, the staff, the lab technicians, and then also, is your data representative, right? If you just have data that represents maybe a specific edge case, it could be imbalanced, then you're not going to be able to make a good prediction. So if you are going to store data in AWS, where are your options available? Well, there's the Amazon Simple Storage Service, or Amazon S3. This is object storage. You can put files as large as 5 terabytes inside of Amazon S3. That's one of the huge advantages of the object storage system. And in fact, it is by its nature a data lake, S3, right? Because it can handle essentially infinite disk IO and infinite storage and infinite compute. And so S3 is really a building block for lots of things. And you can also build, basically machine learning and data engineering pipelines on top of it. Now, another one that's actually very interesting is the Amazon FSx, which is a managed file servers that can deal with mounting a volume that many instances can talk to, and also Amazon EFS or Amazon Elastic File System. These are both managed file systems that are opening up new workflows. There's also, for example, RDS, and RDS is part of a series of different relational database services. This is often a place that people will store data, and RDS does scale, quite well to a very large data sets. And then there's Redshift, which is a columnar data set, which is designed for doing data warehouse type operations. That could be a source of data. And then Amazon TimeStream. This would be if you're going to get a bunch of, let's say, IoT data, you could put it into Amazon TimeStream. Now, ETL is the concept of extract, transform, and load. So you would have data that would live in a data store, potentially S3, or a relational database, or even a third-party database living somewhere else. Your crawler would go through, find all of the data in the schema, put it into a data catalog, and then you would write a transform script that would actually take that and, let's say, rename one database column to another column, or take the data and move it to another location, or maybe rename certain fields. This is the concept of transformation. And then loading is once you've done that transformation, you potentially put it into a new location. Then that new location could be, for example, Redshift, right? Redshift is a really good example of something that could be a data warehouse. Now, ETL on AWS, one of the tools that's probably the most useful for it is AWS Glue. And it runs the ETL process, it crawls data sources, and it even has ML functionality. I've used it quite a bit, and it's actually nice because it can generate both Python and Scala code. So in Glue, in a nutshell, the way it works is you have the Glue service, which is serverless. It can actually talk to S3, Redshift, RDS, pull it all together, multiple data sources, make a data catalog, and then you create an endpoint that can be queried by things like Athena or even Jupyter. And in general, the way it works is that it gives you this Python script that has imports and variables, the download and extract, and then the upload to S3. And then you would build a policy as well that would interact with the different data sources using an IAM policy control access. And in terms of securing the data, you would do data encryption. And in this case, potentially you would deal with repositories that can be quickly and easily encrypted. So you would want to encrypt data both when you're storing it and also in transit. The other thing that is important is, even though it doesn't seem like it's important, is to audit all of the interactions with the data. And this would be something that the AWS CloudTrail can do. AWS CloudTrail can detect unusual API activity, capture it, store it, review it, do compliance auditing, operational troubleshooting, security analysis. So really having a comprehensive auditing system is critical for dealing with machine learning systems. So let's move on into evaluating data next here. And before you actually can understand your data, you're going to have to look at some descriptive statistics. For example, is it in the right format first? Is the customer name right? The transaction name right? These are all things that you need to format. Is it in comma separated value? So this is kind of the data cleaning process. One of the things you could do is you could use a third-party library like pandas, right? So you could say import pandas as PD, put that into a data frame, turn it into CSV, JavaScript, object notation, Excel, Pickle. These are all good formats. And then in terms of pandas, what you could do is you could deal with a pandas data frame and pull out descriptive statistics like the number of rows, number of columns, things like that. What I do a lot is I'll use this columns method to just show me initially when I pull something in, like how many columns are available. Sometimes there's 10 columns, sometimes there's 1,000 columns, and it's important to know what you're dealing with. And then index can show you all of the rows that are available. You also can do .d types, and this will show you each of the types of the columns, and you also can do info, and that will give you information as well. So descriptive statistics is a way to gain insights on the data before you clean it. So you would look at overall statistics. This could be, again, columns and rows. You could also look at multivariate statistics, such as correlations, right? Like, do a heat map, for example. Which things are actually correlated with each other is pretty important. And then you also could look at attribute statistics as well. These are some of the things that are available. And these would be numerical, like mean, standard deviation, variance, minimum value, maximum value, geometric mean, arithmetic mean, those kinds of things. So statistical characteristics, we have wine.describe here would be example. It would just print out everything you've got in terms of the normal descriptive statistics, which is usually average or mean, standard deviation, min. I personally like median. That's one of my favorite descriptive statistics. I want to know, like, basically what the midpoint is of values. And categorical statistics can do things like identify the frequency of values and also look at class imbalances. So this would be really important before you do binary classification to know, like, how frequent each of the classes is. If you have 4,000 examples of one class and 2 of another, now you got a problem. And plotting attribute statistics, this was a great way to visually look at things and look at, for example, a histogram, right, which shows us the distribution. I personally am a fan of pair plots, right? You plot every single thing against everything else. If it's, let's say, 10 or less columns, scatter plots, and again, scatter plot matrix are pretty nice because you can see how a bunch of things compare against each other. You also could build out things like a scatter plot with identification, right? So you could even plot the different values and show even more dimensions to the data. So that's really the idea, is to even look at it not just in two-dimensional form, but into multi-dimensional form, right? Because you can use the size as a dimension, you can use the color as a dimension, you can use facets as a dimension. There's lots of different dimensions you can add to the data, so you can look at things in a very sophisticated way, including 3D as well. That's another way to add dimensions. Correlation matrix is one of the ways people traditionally look at how to get started, right? If there is a correlation with something, then potentially this could fit into a machine learning model. Heat maps are one of the best ways typically to just kind of visually look at things at the very beginning and say, hey, what's going on here? Do we have any signals? Okay, let's get into feature engineering next here. Now, in terms of feature engineering, um, feature selection and extraction, the idea here is that two things that can make a model more successful would include feature selection and feature extraction or creation. And this is about really selecting the things that are relevant and discarding the things that are not relevant or even redundant, and so that you can train your model correctly. Now, in the case of redundant, one of the reasons why this could be important, amongst many other reasons, is computational time, right? Like if it takes a really, really long time to train a model because you have redundant features, that could be a waste of your resources. Also, feature extraction can do things like handle missing data and convert the text data into numerical data. You can also look at duplicates, bucketing, all kinds of different things you do, building new features, for example, encoding ordinal data. So this is categorical data that's non-numeric. It's got to be converted to a numeric scale, right? So if it's ordinal, it would be like low, medium, high, very high. You would encode it into like a numerical category, like, right, 1, 2, 3, 4. Most ML works best with numerical data, and so you got to convert all of it into a numerical form. Encoding non-ordinal data. So this is basically, if there is no order to it, you still need to break it up into a numerical form. And so one of the ways that you can do this is you could do like ones and zeros, right? So red is 1, 0, 0, blue is 0, 1, 0, et cetera, et cetera. One of the things that you can do to clean the data is you can think about things in terms of the type, example, and action. So variations of the strings, medium versus medium, you convert it to a standard text. Variations in scale, so number of doors purchased between numbers purchased, you'd normalize to a common scale. You can use columns with multiple data items, so safe high maintenance or parse into multiple columns. Missing data, missing columns of data could be converted into deleting rows or imputing the data, basically inferring what it could be. And then outliers, there's lots of different things you can do to deal with it, including using machine learning algorithms that are robust potentially against outliers. Missing data can be difficult. And so one of the things that you could figure out is, why do you have missing data? A lot of ML algorithms don't like it when you're missing data. So you have to figure out what it is you want to do with it. Like, you could count the number. If you say in pandas, df is null.sum, you could count the missing values for each column. If you did df is null.sum axis 1, count the missing values for a row. And then what are you going to do now? So now that you know you have missing data, well, you could drop or impute the missing values. And you could also say, what were the mechanisms that caused the missing values? And are these values missing at random? And then also, are there rows or columns that you're not aware of, right? So these are some of the things to consider. All right, so this is a pretty big section here of data. I'm going to have to break it into pieces and cover the part 2 next week. So I'll go ahead and stop screen sharing. So this was a good overview of a very deep topic, right? Which is kind of building through your initial SageMaker pipeline. And then next week, same time at 4 p.m. Eastern time, I'll cover part 2 of this, which is building SageMaker pipelines, and get into the details a little bit more. All right. See everybody next week.